So we've spent a good amount of time sort of thinking through the conceptual aspects of acid-base chemistry and the mechanics of solving for pH and equilibrium concentrations. Um, but what I'd like to do quickly is connect all of these sort of mechanics and concepts back to some of the fundamental ideas in chemistry and really think about what is the chemical origin for the strength of an acid as it relates to like the bond strength. So let's start with this series here. So these are all the halogens, these are the group 7 elements, fluoride, chloride, bromide, iodide, and strength is increasing from left to right. So HF is the weakest, which is considerably weaker than HCl, which is considered an actual strong acid. HBr is even stronger, and HI is the strongest. So how can we think about bond strength or polarity or the size of the resulting ion as it relates to strength? So if we harken back to Chem 107 ideas, we can think about that series and know that fluoride it's really, really tiny, and it's the most electronegative atom on the periodic table, which means it's going to hold on to that positive ion really super duper tightly, and in which case the bond strength is going to be greatest for HF and it's going to be weakest for HI. And hopefully that intuitively tracks with the strength of the acid, because the acid strength is really how capable is that molecule of dissociating or donating that proton. Of course, it's going to be easier to donate that proton if the bond itself that's holding the proton to the ion is intrinsically weaker. And that tracks with this other periodic trend where as we move down a group in the periodic table from fluoride all the way down to iodide, iodide is enormous relative to fluoride. And because of that, it's a much more stable ion in solution. It's happy because those electron clouds are very dispersed and far away from the nuclei in the center of the atom. And so we get this sort of similar tracking where the larger the ion that's left over after the proton leaves the acid, the stronger that acid is. And that's simply because larger ions are just easier to stabilize. And the final attribute I'll mention is electronegativity, which directly correlates with this idea of polarity. So remember, electronegativity is the capacity for an atom or an ion to draw electron density towards itself. And the most electronegative atom on the periodic table, or the direction of the periodic trend, is towards the top right. So fluoride is the most electronegative, and then elements down in the bottom left are the least. And so fluoride is going to be more electronegative than chloride, which is more than bromide, which is more than iodide. And so electronegativity is really just another proxy for bond strength, because the more electronegative you have, the stronger that's going to be held, the more tightly it's going to be held to that fluoride ion, meaning it's going to be less likely to donate that proton, meaning it's a weaker acid overall.